Hi folks, today we're going to talk a little bit about some mechanisms of electron transport. And some of these mechanisms are seen throughout the electron transport chain in different complexes. For example, we're going to talk about NADH transfer onto FMN, which happens in complex 1. Remember that the prosthetic group FMN flavin mononucleotide actually accepts the pair of electrons that's moved and causes FMN to become FMNH2. This is very similar to what happens with FAD, and then NAD is oxidized to NAD+, or NADH is oxidized to NAD+. We're also going to talk about the handoff model from FAD or FMN, H2, onto the iron-sulfur relay. This happens in complexes 1 and 2. The iron-sulfur relay serves as kind of a wiring to move electrons from the active site of oxidation of the cofactor all the way up to the site of reduction of the reduced cofactor, which happens in the next step. That would be FeS onto Q to form QH2. So this would be taking, for example, iron 2+ to iron 3+. And so that's going to be a 1 electron transfer, as is this one. So we're going to talk about those different mechanisms. It's pretty easy to think about this, but we are going to have to kind of walk through some of these steps one at a time. Okay. Now, we're also going to see QH2 dropping off electrons in complex 3. This also happens. This guy happens in complex 1 and 2. And finally, complex 4. Or I guess not complex 4, but step 4 would be the QH2 being oxidized to Q by dropping it onto, I suppose, Cytochrome C via a heme group. Okay, so we're going to be handing off 1 electron at a time to do this. So I guess we go through a QH semiquinone intermediate and then a second 1 electron to Q, and those would be handed off onto Cytochrome C to take it from 3+ to iron 2+. So we're going to go through each one of those here step by step, and we will watch how the mechanisms can be different depending on which cofactor we're looking at. All right, so first we're going to do the reaction that happens in complex 1. And remember, that's NADH dehydrogenase, where our NADH is going to pass 2 electrons here onto FMN, flavin mononucleotide. The isoalloxazine ring here, the 3 fused ring systems are here. And remember that our group is a mononucleotide. That's why this is flavin FMN, not FAD. In FAD, that would be a dinucleotide. Okay. So the push here is relatively simple. We're going to be pushing a whole pair of electrons, which means we're going to be moving a hydrogen and its 2 electrons, giving it a negative charge. And that's going to be one of these 2 up here at the top of the molecule at the sp3 position. So to do this, we're going to try to form an aromatic ring. We're going to push through this, and we're going to push off one of these hydrogens. And we're going to put those here onto the FAD ring. Okay. And when we do this, we're going to break octet if we go any farther. Remember that this nitrogen already has a lone pair. We're going to exceed 8 electrons. So to avoid that happening, we're going to have to push electrons through the ring, and we're going to use this to attack the hydrogen in solution, a proton, right? And notice the balanced equation, we have that proton going together with NADH at all steps. So we're going to form the products NAD plus with its R group. And we're going to have FMNH2. It's going to still have the same structure over here. The nitrogen at the top of the ring right here is going to have a hydrogen on it. That's one of the H's in FMNH2. And the other hydrogen is going to be down here at this position. Okay. So this is simple pair pushing, the kind of thing that you should be relatively familiar with and comfortable with from like an organic chemistry class. FMNH2 and NAD+. And remember that this is a prosthetic group, this FMNH2, which is going to accept the 2 electrons and then trickle them out one at a time onto the iron-sulfur relay to transmit them through the protein, right? Which is a very common theme in electron transport, is that those electrons get moved one at a time through an iron-sulfur cluster region. All right, so now we're going to start to see something a little different. This is, for example, the second part, the second phase of complex 1. Though it also happens in complex 2 via an FAD. The chemistry is identical because they have the same isoaloxazine ring. The only difference is in that R group down here, which is, remember, either a mononucleotide for FADMN or FMN and a dinucleotide for FAD. Okay. So we're going to be moving one electron off, and it's going to come from both of these two positions, the electron. So one from each side, presumably, right? So what we're going to see happen is dropping a single electron onto these iron-sulfur clusters. Remember, these are irons and sulfurs, so they can go between the reduced form Fe2+ or the oxidized form Fe3+, right? If it's going to accept an electron, it needs to be in the oxidized form, and if it's going to give up an electron, it's going to be in the reduced form. Right? So if it's reduced, it's going to pass its electron off to the next one in the relay, just like, you know, a regular old relay race, right? We're going to just be passing this up and ending up typically onto coenzyme Q, which we're going to talk about in the next phase of this video. But keep in mind here that what we're going to be doing is pulling electrons here, and these two guys, FMN and FAD, have a stable semiquinone form, which means they can hold onto a radical. It's delocalized across a couple of atoms, which means that you can hold onto a radical in a way that NADH or NAD cannot do, right? So we can do one electron transfers here, like we're going to see, and two electron transfers like we just did in the first part of this video, okay? So what we're going to do, remember with radicals, we have the fishhook arrows, so we're going to be dropping one electron here. So here's our first electron, and we're going to be dropping the other electron onto the nitrogen, okay? And then this poor hydrogen is just going to be lost as an H+. Essentially, its glue broke, and now it's not held on anymore. It doesn't have any electrons. It's now an H+, and it's given up to the solution. Okay. And this is going to cause the transformation of this molecule into the semiquinone. And if you recall, radicals like these have resonance forms. And so we're going to be able to split those guys over a few different atoms to stabilize the radical. So we're going to be able to spread that radical character out over the molecule itself. Okay. So what we have right now is a dot, a radical nitrogen. We also have this double bond here. And so if we wanted to, what we'll do is split out here the electrons to rearrange them. Okay. So this is what we would call FMNH dot. But because it's resonating, we're going to draw the other resonance form for the radical. And notice that essentially what we've done here is homolytic bond cleavages, which gives us partial radical character here on the carbon. We're just rearranging lone electrons to spread them out, okay? And so we have partial radical character up here on this carbon, partial radical, and we have partial radical character on the nitrogen. Now, typically, radicals are more stable when they're on larger atoms. Both nitrogen and carbon and oxygen are in the same period, so there's really not a lot of difference in terms of energy level. They have more electrons. Electronegative elements like nitrogen and oxygen typically want electrons more, but they are still very reactive, right? And so we're going to see a rearrangement of them into these positions. We have both a nitrogen radical character and then also a carbon radical character. But the nice thing about this is in this particular form, if we give up our second electron to the relay, then our other electron can recombine to form a double bond in the ring to give us a conjugated ring system. And that will form our final complex, the FMN itself, or FAD itself, depending on which complex we're talking about. Carbonyl nitrogen. Oops. Nitrogen. FMN. That looks good. Okay. So now we have gone between our FMNH2 or FADH2. They're literally identical mechanisms to FADH dot or FMN dot, to FMN or FAD itself. Okay. So we drop one electron to the relay, it zips up to the next place it goes, typically onto a Q in complexes 1 and 2. And then we drop a second one out of the semiquinone form, the FMN dot. Onto the relay again, it zips up the chain, and then it reduces us all the way down, or oxidizes us all the way to the FMN or FAD form. So here's the other end of that relay. Our electrons have been zipping up and down this, this chain. So for example, we just donated our electrons here onto the relay. Here are some more iron-sulfur clusters, or maybe the same ones. They're just going to zip down. And then we have to drop them onto an acceptor, one at a time. And luckily, coenzyme Q, ubiquinol, or ubiquinone, depending on if it's the Q or the QH2, which is ubiquinol, okay, is going to be able to accept 1 or 2 electrons as well. Okay, so what we're going to do first here is we're going to drop it onto a high-energy pi bond. So we can rearrange it. We also want to, if you notice here, we don't really have hydrogens to lose in our pi system. So what we're going to do is drop it in such a way that we give the radical to a stabilized resonance form. Okay, that's a really important thing we want to get here. Is one, we want stable resonance forms for the radical. And we also will be developing a negative charge. And we want to develop that on an electronegative element. Okay. Now, obviously, the electronegative element we have here is oxygen. So we're going to be taking electrons to make a pair, okay, and then we're going to split them in such a way that we get the most stable resonance. Now, our two choices are to stick the negative charge onto the oxygen and the carbon, the radical onto the carbon here, or we could put the negative onto the carbon and the radical up here onto the oxygen. If we do it with the radical on the oxygen, couple problems with this. Number one, well, everything looks fine, right? We have a new, I guess we never, let me redraw this so it's a little neater. There's our radical. We would have a carbon with a negative. We, of course, could delocalize that charge, but the electronegative element wants the negative, right? So we could also have placed it with a radical here and a negative up there. Okay, so that negative charge up here on oxygen is a favorable system, and we can still resonate the radical. Okay, so we can do resonance in either form, but the radical is more stable when it's spread out, right? The radical itself is a violation of the octet rule, right? So we want to spread that around as much as possible, and the oxygen gets the negative. So when it comes to chemistry, remember, there's no intelligent stuff going on here. It's just following the principles of stability and physics. And so this right-hand form is going to be the best form. So when we draw our product here, we're going to form the semiquinone. So that's that. I'm going to leave a lot of the other side stuff off because the only important stuff happens here on the rings. And a key thing to remember here is that when we get a negative charge on an oxygen, it's a good strong base, like an OCH3 or something. So we're going to tack a hydrogen. Okay? And this is going to give us this form. And of course, with a radical, we have resonance forms for that. Okay, so we can delocalize it throughout the ring. For example, we could go this way. We'll steal an electron from the pi bond and split this one out onto the side. So we would now have radical here. Okay, or I suppose we could go the other direction. Let's see what other choices we could have taken here. We could have gone this direction, recombined, split out. Okay. So we would have had something like this. Yeah? Or we could finish this out by finishing the ring. Okay, so I'm going to show you guys kind of how that's going to look to finish out the ring. We want to form the aromatic ring if we can, so I'm going to take one from the pi bond, put one up on the oxygen. We're going to form a ring, and the same thing can happen here. And so we're going to end up with effectively the fourth resonance form, which is going to be a full stable benzene ring. Obviously, that's going to be the most stable of the contributors because, again, we have aromaticity and we have a radical oxygen. So this is what we're going to call QH dot, and that's going to be part of the radical resonance system. So QH dot is the actual name of this very handsome semiquinone. Okay. So we end up with the QH form. Again, I've left off the side chains and all that stuff here. Just keep in mind that that's still happening. Now, we're going to get a second electron coming down the relay. And that's just going to pair up with that oxygen and going to give it a negative charge. And what do we see when we get oxygen with a negative charge? We usually attack a hydrogen. So we're going to form the QH2 or ubiquinol form of this cofactor. And again, all this stuff is still on there. QH2. Great. Okay. So keep in mind that that's what's going on here. When we're dropping electrons one at a time from the iron-sulfur relay, we're going to drop them first to form the QH radical, which is kind of here in the middle, and then we're going to drop the second one onto QH radical to form the QH2 reduced cofactor here. QH2 versus QH versus our original ubiquinone Q. So Q, QH, QH2. So finally, we're going to see the dropping of QH2 onto Cytochrome C through an iron-sulfur relay. This happens in complex 3 of the electron transport chain, where ubiquinol is going to drop off onto the oxidized form of Cytochrome C, and it's going to turn it into the reduced form of Cytochrome C. And ubiquinol is going to go through a couple of intermediates, I guess, one intermediate, where we're going to go from QH2 to a QH dot to a Q. Okay? And so we're going to need 2 cytochrome Cs to do this, right? Because each cytochrome C can only hold a single electron before it's full. And so we're going to need a second one to come and take it from the QH dot. Okay? So I'm going to show you the mechanism for that. Now, when these come into close contact with each other, a spontaneous zap of electrons happens, right? They move. So what we're going to see here is an electron coming from the OH bond. First electron is going to go here. Second electron is going to drop onto the oxygen to form our QH. Okay. So again, I'm going to leave the side chains off of this. This is our QH dot. Okay. And it has a radical. Now, of course, that radical can be essentially, delocalized. It's a resonance form. So I'm going to show you all those radicals again, all those forms. But keep in mind that they're the same as before. So we're going to form the double bond O here, split the radical out into the ortho position, as it were. Of course, this is a fully aromatic ring, so it could also end up over here on the other side. I'm just going to do one side of the resonance forms here. You get the idea, hopefully. If you have questions, you can let me know. Okay. There's going to be also a fourth position here if we went the other direction. That's going to look a little bit like this. Nope, not like that. Yeah, I guess so. So these all can interconvert. So that's our QH dot. Okay. Then we're going to be dropping our second electron onto the relay. And again, that's going to be coming here from the OH bond. Once an empty spot opens up and this becomes an Fe3+, there's an open gap, so we're going to drop the electron. And we're also going to be taking the electron and reshuffling it. So maybe the right form to think about this in would be in this particular resonance form right here. Because the OH, as you can see, is right next to that radical. And that means we're going to get a termination. Okay. So but realize that these are all one resonance hybrid. Really, we're going to see partial radical character here, partial radical character orthopara, and an OH down here. And we're going to have resonance all the way through that. So partial, that's what the real resonance hybrid looks like. So it doesn't really matter which form we do it in because they're all exhibiting partial radical character. And once we do a move on it, it's going to effectively terminate. Okay. But the key thing here is that we're going to be pulling off of this oxygen hydrogen bond, breaking that with the second electron. And the other one is going to form the bond with the next door neighbor radical. Okay. And that's going to give us our QH2 form. Or in this case, our Q form, right? We're not going to go back to QH2. We're just going to go back to coenzyme Q, ubiquinone. And of course, all the delightful side chains. We have 10 to 12 of those. And that would be our coenzyme Q, ubiquinone. Okay, so I hope that this video is helpful in thinking about different ways electrons can be moved from one place to another. This is typically the way we see electrons transferred in the electron transport chain. Please let me know if you have questions, and I'll see you next time.